Teresa? Yes. 29? Okay. Sure. So 29 says find two functions f and g such that the composition of them is something like this. So there's lots of answers you could give here. So the idea, the way I would think about this is I would try to think about finding like an inside function and an outside function, because that's really what's going on with the composition. So what I see for an inside function would be x squared minus 1. And an outside function I see as sine. So my f of x is the outer. So that would be sine of x. And my inner, that's my g of x, would be the x squared minus 1. And I can see that when I put x squared minus 1 into f of x, I get exactly this, right? This is one possible answer. There's lots of possible answers, though. What's the cheatiest answer you could possibly give in a problem like this? There's one answer that always works, and it's really trivial. Yes, very good. So you can always take advantage of, like, the identity function for composition is just whatever of x equals x. Because when you do that composition with anything else, it just returns the exact same thing. So it wouldn't matter whether you did f of x or g of x equal to x, and then the other function equal to whatever you're trying to get. But that'll always work. That's a cheap, like a cheap way of doing it. But it works. It follows the directions. There's nothing in the directions that says you can't do that. So that works. That's fine. Another one, you could do f of x is equal to sine of x minus 1. And then g of x could be x squared. Right? You could have done that. That would be okay. Again, you only need one answer for this. Any of these answers are fine. I'm just kind of talking through like how you would do this and making sure that people realize that there's lots of things you could do. I'm trying to think if there's anything else sneaky here that I could, or anything else that's kind of obvious that wouldn't be overly sneaky to do. Nothing stands out now, but these are four relatively, or three, I guess. Well, I mean four if you count this one being, there's really two ways you could have written that, right? The x could either be f of x or g of x. It doesn't really matter. So there's some answers that are all reasonable, that if we looked at what everybody did, probably somebody in the room had tried doing something like one of these three or four. Come in. Hi. How are you?
Good. How are you?
I'm okay. Krista, you got some stuff here. You're welcome. Others from this. Teresa, you feel happy with this, though? Okay. Elizabeth, right? Yes. Shh. Okay. So can I just give you an example of something that is one-to-one but not onto, and then that is onto but not one-to-one, and then something that's both? That's probably going to be the most practical thing than rehashing the definitions. Does that sound okay? So I'm going to use mapping diagrams to do this because I think it's the easiest to kind of see. Oops. Okay, so this one is one-to-one, because the y coordinates are all getting used just one time. But it's not onto because we have a y coordinate that isn't used. Okay with that idea? Okay. Oops. This one is not one-to-one because we have y coordinates that are used more than once. But it is onto because all the y coordinates are used. Okay with that? Now, if you want something that is both one-to-one and onto, it's going to look like something like this. So each y coordinate is used one time, and all the y coordinates got used. So it is one-to-one and onto. Does that feel okay? Okay. What would this look like graphically? That's a little bit more challenging to think about. So if I look at this, let's start with the easier question. Is it one-to-one? No, right? Because if you draw any horizontal line, well, almost any horizontal line, it's going to intersect the graph in two places. So that's like x1 comma y, but this would be x2 comma y. The point is that they're the same y. So you have a y coordinate that's being used more than once. Okay with that, Elizabeth? So we know that this is not one-to-one. Okay there. As opposed to, say, something like this, that certainly is one-to-one, right? There's no horizontal line you can draw that's going to intersect that graph more than once. Okay with that? And now, certainly we know that this diagonal line is onto. How do I know that it automatically that it has to be onto? What's the range for it? All real numbers. Could I possibly miss any y coordinates if I have all real numbers for my range? No, right? So this is definitely onto. Yes.
So if there's like a break in the range, it's not onto.
So here's what I would, not necessarily. So with the graphs, it's a little bit, how do I want to say this? In this kind of a class, if you're given a graph, your assumption is whatever the range of the graph is the range for the function. So like even if there's a gap in the range, it doesn't necessarily mean it's not onto it. Really, like when we're just drawing the graph of the function, we're like eliminating a lot of information that you would need in order to determine if something is actually onto or not. So it's not really a question that I would ask you from just a graph. Because really you need to know like what set are we mapping to in each case. When we talk about the graph, this set that we're mapping onto, we just call whatever the range is. We just use the range from the graph as whatever that set we were mapping onto. We're not necessarily saying, oh, I'm mapping from the reals to reals. And then the range for this is like 2 to positive infinity, so it wouldn't be onto it. Like, we just don't do that in this kind of a class. If you took like an abstract algebra class or something as a college student, that would be something that you would be much more specific about. But it's kind of beyond the scope of what we're really needing to deal with here. So if you're looking at a graph, unless we tell you you know, this is the graph of a function that maps this set to this set, and then you can compare the range to whatever the set you're mapping onto. Like that's something feasibly we could do and talk about. But you would need that information more than just the picture. Now I probably over-explained that, but I wanted to be clear about it because it's kind of a hard question to ask, right? Yeah, and a good question, because you should look at that and go, how would I tell looking at a graph if it's not onto, right? Like if there's y coordinates that aren't used, does that make it not onto? Well, you know, it kind of depends, unfortunately. But it's not a question I would ask you guys. Anybody else? These have been good questions, guys. Elizabeth, you're happy with the difference? You feel good now? Okay. If you're not, like, let me know and we can do more. But it felt like just some examples was going to be more helpful than rehashing definitions or whatever. Yeah, sometimes just doing the problem, you're like, oh, okay, I get it. Kristen, what's up? 28. Sure. So 28 says, using your result from question 26, find the composition, or find G compose F of negative 3. Do you have an answer for 26 that you can tell me, or do we need to do it? Okay, that's fine. I'm just checking. Okay, so 26 says this. So if I do G of F of X is what we were asked to do, one of the things we were asked to do in 26. So that's G of F of X. So I like to start by replacing F of X with the expression that it's equal to. And then I will plug that expression into the function G. So I have here. Okay. So that's 26. Now if I want to do G compose F of negative 3, all I'm going to do is plug negative 3 in to that function. And when I simplify that down, I just get 1 over 6. Yep. The other way you could think about this problem is G of F of negative 3 is the same thing as G of F of negative 3. So I could start by plugging the negative 3 in for X here, and then use that result to plug into G. You could also think about it that way. But since it said using your answer from 26, I figured that this is really what they wanted you to do. Does that feel okay? Yeah. But either process is fine to do. I just was following their directions. Oh, I don't know your name. Can you tell me your name? Haley. 42. Thank you. Yes. This is the one you can't read, right? Is that why we need to do it? Just skip it. Okay. Okay, you can't read the points. I don't know what they should have been. It's a crappy picture on my part. We're just going to skip it. Feel okay with that? That was number 42. Because you just can't read the information that's on there. Makes it pretty impossible to do anything with it. If you could read the points, should be a relatively easy question to do, right? You just can't read them, so we'll see if I can get a better picture in there for next year. I'll put it on my to-do list. I just never seem to be able to get to everything. Is that okay, Haley? Yeah. Okay. Anyone else? Okay, fair enough. What I'd like for you guys to do is, if you don't have your tablet out, please take out your tablet and open up your OneNote to the shared notebook in the content library for our class. In that content library, you'll see a page labeled Chapter 1 Homework Quiz 1. I'd like you to copy this page into your section of your notebook and answer these two questions. We'll take 10 or 15 minutes to kind of do that, and then I'll tell you how to turn this in. Okay? Just two problems. Yep. The idea with the homework quizzes is I just, just a couple of minutes. I don't want to take like all day doing one of these things. You know what I mean? Yeah, anywhere in your section of the notebook is fine to put it. We're actually I'm going to make a Dropbox for you to turn this into. Well, if you do that, you're going to have to take a picture and then drop it into your OneNote and publish it as a PDF, but you're welcome to do that. And again, keep in mind that since this is a OneNote page that you have, you can go in here and like make more space in between the questions if you need to by pressing, you can press enter and make more space. Some of us write bigger than others. Just want to give you a heads up on that. In general, when I give you stuff to do like this, I'll try to make sure they're OneNote files so you can make more room for yourself so you're not if you write big, sometimes you run out of space. You guys know how it is. I'm sure you've had classes where it's like, this is not enough space for me. And things got messy. And it's hard enough to be neat on the tablet, right? So I try to make these lightly editable for you. So if you need to alter the spacing, that's okay. Yeah, sure. I mean, you should know what the square root of 1 is, though.
Oh, yeah.
I mean, it's not wrong to have a square root in there, but you know what I mean. It's 8 o'clock, so I get it. I get it. Sure.
Hi, Mr. Kulik.
Hi.
A bagel with cream cheese or a cookie?
Yeah, let me look at what the options are. How are we doing, guys? Okay, so you want to talk about how to turn this in? So even if everybody's not finished yet, let's take a pause and I'll explain to you how we're going to turn this in. What we're going to do is we're going to publish this to a PDF. So the way you do that is you go to the file up here in the, where's my mouse at here? In the upper left-hand corner here. So go ahead and click that file tab. On the left side of the screen, you see the word export. Go ahead and click that. The file format you're going to use is a PDF. And then you just hit the export button. That'll prompt you to save it to a location. I would just put it in the desktop so it's easy to find later when you need to delete it or whatnot. Once you do that, you'll just put it in the PowerSchool Dropbox that I made for this assignment. And that's all there is to it. Everybody okay there? In general, from here on out, if we're turning anything into the PowerSchool Dropbox, I'd like it as a PDF file. It makes it easier for me when I'm grading things and passing things back if I have the same file format from everybody. Yes, sir. Yeah, so if you took a picture, just drop that picture file into your OneNote and publish it as a PDF. Yep, exactly right. So even if you took a picture, just drop that picture file into a OneNote page and then publish it as a PDF and turn that thing in. And that's good. Yep, good questions, guys. As that's hopefully not too hard to get a PDF out of something, right? Why do you suppose as an aside, why do you suppose I prefer this file format? I can't edit it, right? So it's difficult to edit, so it makes it easy for me to grade on. And then if I have to erase something, I know I can't erase any of your writing. And then if there's a disagreement over whatever, it's, I can't change it. I know you can't change it from that point. So it is what it is. In general, if I'm a student, that's the file format that I would turn anything in. But I know some teachers probably request different things. This is what I like. Is anyone still working on getting things turned in here? Okay. We'll take 5 or so more minutes here for those of you still kind of picking away at things. Those of you that are finished and waiting patiently, I appreciate that, and giving people that are still working a chance to kind of work in peace. That's very kind. Hi, Krista. Okay. Okay. So go to export here on the side. And then you're going to pick the PDF option. You may. and then just hit export. So this is going to prompt you to save it somewhere. I would just put it on my desktop so it's easy to find because you can deleted it after you've turned it in. And then you go to the Dropbox and boom.
Thank you.
Yeah, you're welcome. Pretty easy, right? You'll do it a bunch more times this year, I'm sure, so we'll get good at it. But that's one of the nice things about OneNote is it's easy to make a PDF out of whatever you have there. Like, do you guys have journals to write for your English class? Do they require you still to handwrite those things? Not anymore. I would have handwritten them on my tablet. Been like, take this and then published it as a PDF. It's like, it's the same as non-handwritten. You know what I mean? I probably would have gotten in trouble. But notebooks are heavy. I don't carry around an extra notebook. I'm just going to carry it on my tablet. You know? You're back. Yes. If it's in the Dropbox, the file, the way they name the files, I can tell whose it is immediately. So you don't have to worry about writing your name on it. Yep, no big deal. That's one of the reasons I like using the Dropbox also for this kind of stuff is it names all the files for me in a way that I know whose it is. How does it do it? It names the file with your, whatever the name is you have for PowerSchool, and then like the date, and I think even maybe the time it stamps the file when it gets submitted. So it's easy to do that. So don't worry if you didn't write your name on it. I know. And I grade them in OneNote, and I'll put it back in your notebook when I finish grading it and stuff. So if you go look later, probably not today, but by next week, if you go look in your OneNote, you'll probably see a new page with that graded homework quiz in it. Is everybody finished here, Kristen? Sure. Anthony, you're finished? Okay. Anybody else still working? I'm picking on you because you said you needed a minute before. Okay. So let's finish up here. We have one more section in Chapter 1 that we're going to finish up here today. So that means that the Chapter 1 test is coming up here in the not too distant future. So if I were to estimate for you guys, well, we have 2 class days next week. So I think your test date would be the following week. I think 4th hour gets their test next week. Okay, so in this last section, section 1.8, we're going to be talking about graphical transformations. So we're going to take a minute and get in our math time machine and remember back to geometry and recall that there are 4 types of graphical transformations. Does anybody remember any of those 4? I know geometry was a long time ago. Or reflection is one of them. Good. And I think somebody was saying rotation also. So those are both one of them. There's actually 2 types of reflections that we're going to worry about. We can reflect across the x-axis or across the y-axis. There's what's up? Yes, translation's another. There's actually lots of types of reflections other than those 2. Like you can really reflect across any line, whether it's horizontal or vertical or diagonal. But in this course, we're just going to really worry about those 2 types of reflections. There's translations, and there's one more. Dilation. Very good. So if you remember, again, back to geometry, oftentimes when we did this, we described these with like a transformation map or like something that looked like this, where our original point, we, in the case of a reflection, you negated one or the other coordinate. Rotation, we didn't actually do this for in geometry, and we're not going to do it now. I think without the aid of linear algebra, this is a rather difficult thing to ask. Translations. All we did was we added some constant to the x or y coordinate. And then dilation, we multiplied the x and y coordinate. Now, I think in geometry, your dilation was always symmetric, where you multiplied the x and y by the same factor, but there's really no reason you would need to do it that way specifically. So I'm going to write them as 2 different letters, keeping in mind that like they could be the same letter still, right? Like there's no reason A and B couldn't be equal. Now, I don't expect that we all remembered these transformation maps off the top of our head, but I hope that we recalled that we did do this in geometry, and we made we took a triangle and we moved it 3 units over and then reflected it or something, and you did that by kind of altering the coordinates for the vertices of the triangle. That's all I'm hoping that we remember. Is that okay? All right. So this was relatively easy to do if all you're worrying about are like the vertices of a triangle, right? If now our set of ordered pairs instead is like the set of ordered pairs in a function, this becomes a little bit more onerous, and we're going to develop a little bit different notation that doesn't require us to deal with dealing with this for like infinitely many ordered pairs. So let's say we have a function y equals f of x. Oftentimes, this original function we refer to as like a parent function. That's a term that we used a lot last year in your Algebra 3-4 class. A transformation, I shouldn't say a, we can say any transformation of f of x can be written as g of x equals a times f of 1 over b x minus h plus k, where, and then we're going to describe what each one of these coefficients are going to do in terms of a transformation. And this should look relatively familiar from last year, right? The only difference probably is we didn't ever deal with a coefficient inside of our function last year in our Algebra 3-4 classes, but this a times f of x minus h plus k is something that we kind of saw a bunch of times last year, right? Usually the f was some specific function, like a logarithmic function or a square root function or whatever else, but here I'm just going to use the generic f of x. Okay, so a does two things. So if a is positive, we have, let's start with a is negative. We have a reflection across the x-axis. If a is positive, we have no reflection. Across the x-axis. And a can't equal 0 because if it's 0, we don't really have a transformation of f of x. You just have, a horizontal line, which is not really what we're interested in. The other thing that a controls, the magnitude of a has some effects. So the magnitude of a is greater than 1. We have a vertical stretch. That's a type of dilation by a factor of a. If a is less than 1, we'll have a vertical shrink by a factor of a. And if the absolute value is equal to 1, we have no vertical dilation. So far, so good. Hopefully this rings a bell, right? We probably did this last year in algebra. The b, similarly, also controls two things. If the b is negative, we have a reflection across the y-axis. And if the b is positive, we have no reflection across the y-axis. If the magnitude of b is bigger than 1, we have a horizontal stretch by a factor of b. And if that magnitude of b is less than 1, we have a horizontal shrink by a factor of b. And then we have the h and k. So if h is positive, we translate right h units. And if it's negative, we're going to translate left h units. So that's our translations. And then k, similarly, except up and down. So if k is positive, we're going to translate up k units. And if k is negative, we're going to translate down k units. Okay. So there's two kinds of things that I expect you guys to be able to do with something like this, or to do using this information. Hi again.
Hi.
Kristen, for you. You're welcome. Okay. So, given that f of x is 3x squared minus 4x plus 1, I could ask you to find a function that meets certain criteria, a transformation of that f of x function that meets certain criteria. So, reflecting across the x-axis tells me that my a should be negative. Everybody okay there? Horizontal stretch by a factor of 2 tells me that the b should equal 2. And shift left 3 units tells me the h should be negative 1. Everybody okay there? Since since there's no vertical stretch or shrink and the a needs to be negative, I know really that means a should be negative 1. Yes. I meant to write x. So thank you. Yes, you're correct. I appreciate you pointing that out. I meant to put an x there. My mistake. So thank you. That certainly makes a heck of a lot more sense probably to everybody involved when we have the right things written down. So again, if you see something that doesn't make sense or you think I've made a mistake, please let me know. And you did an excellent job identifying this before we got like all the way through the problem and then had to go back and fix a bunch of work. So I appreciate you catching that early. Okay. So what I'm going to do is I'm going to use this general form for my transformation and plug in my values. Oops, missing one. Everybody's okay here? Okay. And I can clean that up a little bit by distributing the 1/2, and the negative of a negative makes a positive. Everybody's so far so good? Now I just need to do negative f of 1/2 x plus 3 over 2, where this is my f of x, right? So I'm going to plug that expression in for f of x. So I have my negative 1, and I have 3 times 1/2 x plus 3 over 2 squared minus 4 times 1/2 x plus 3 over 2 plus 1. Is everybody okay with that? Okay. So if I distribute, I need to FOIL this out, right? That piece that's squared, and then do a bunch of distributing. I'm going to do all of this kind of in my head, if that's okay with you guys, instead of showing all the distributing and all the foiling and all that nonsense. Is that okay? So let's see. I have negative 3 over 4 x squared minus 3 halves times 3 is 9 halves x 9 over 4, 27 over 4 minus 2x minus 6, oops, sorry, plus, and then that's minus. I think I did that right, I hope. And then we just need to combine some like terms, right? So negative 9 over 2 plus 2 is negative 5 over 2. And then negative 27 over 4 plus 5 is negative 7 over 4, I think. Again, my expectation would not be that you guys are necessarily able to do any of these things in your head that I just did. This is the power that you get from being a math teacher for like 15 years, is that you can do trivial algebra in your head without having to write it down. It's one of the many, many perks of this job. If you certainly need to write down and do more steps and like make common denominators and like FOIL things out and be slow and careful about it, please do that. Okay. And if you are not sure, like when I do simplification like this, like, whoa, you just did a bunch of stuff there, like, can you walk through that a little bit more carefully? I'm happy to do that. That's why I checked a bunch of times before I went ahead and did it in my head. Yes, sir. Okay. That's my favorite kind of questions, are the ones that like we're ready to ask and then you're like, oh, I still got my answer. Isn't that satisfying when you see it yourself? I love it. Not that I'm unhappy to answer your questions, but I think it's like a great aha moment as a student when you're like ready to ask a question. You're like, nope, I got it. No? I can't ever tell because of the mask. I can't tell if you're smiling and like going, oh yeah, I don't know. Yes, sir. Of course. Everybody's okay with one of these though? It basically just is some tedious simplifying at the end, right? Okay. The other thing that we might do is ask you to describe a transformation in order. Let's talk about the order of a transformation. So when we say this, we talk about the order of the transformation. What we're talking about is like if you're actually going to draw step by step, take the graph, like what part of the transformation would you do first to the graph? If you're going to do like, oh, there's 6 things that go on, like what order should I do the transformation so I get the correct picture at the end, because that matters. The order should be the reflection across the y. And then the second thing should be your horizontal stretch or shrink. Oops. The next thing should be your reflection across the x. And your vertical stretch or shrink. And then your translation left or right. And lastly, your translation up or down. So the order in which we're considering these coefficients is the first things we do is talk about what C does, and we do what A does, and then H, and then K. So, given a parent function, f of x equals x cubed, pf is just me abbreviating parent function. Describe the transformation in order for g of x is equal to 2 times x plus 1 quantity cubed plus 4. So what I would do here first is I would translate this into just like an f of x notation. Since x cubed is our f of x, our g of x I could really think of just as 2 times f of x plus 1 plus 4. Is everybody okay with what I did there? Hopefully that's easy to see, right? Sometimes that could be more difficult to see, but in this case it should be relatively easy to see what I did. And what I want to do now is I know that my general form for my transformation should look like this. So I want to rewrite my g of x so that it looks like that, so it's easy to pick out the values for a, b, h, and k. So notice that there is no coefficient here on my x. So really my b value is just 1, right? And notice I have a plus sign here, but a minus sign here. So I would really have plus a negative. So now it should be easy to see that my a is 2, my b is 1, my h is negative 1, and my k is 4. Cool with that? Okay. So, since b is positive, we have no reflection on the y. And since the magnitude of b is 1, we have no horizontal stretch or shrink. Since a is positive, we have no reflection on the x. And since the magnitude of a is greater than 1, we have a vertical stretch by a factor of 2. And then since h is negative, we go translate left 1 unit. And since k is positive, we translate up 4 units. So if we're asking for the description in order, I'm looking for something like that. So even if nothing happens, I'm describing why I know nothing is happening, right? Okay. One more type of problem that I'm going to ask you to do that we'll do an example of, and then that'll finish us up for this section and then the chapter, which is pretty exciting, right? No, it's too early to get excited about anything. I get it. You know what? I don't know why I keep doing that. Oh boy. Maybe that's why I keep doing that. Those of you that write in OneNote, you can make your own XY axis so that it's actually straight. I have a devil of a time drawing straight lines. Okay. So to do this, what I'm going to do first is I'm going to determine my values for A, B, H, and K. So hopefully you guys can see that A is 2, that B is 1, that H is -3, and K is -1. Is everybody okay with that? Now what I'm going to do is I'm going to approach this kind of like like that geometry transformation problem that we did way back in geometry class, like years and years ago. So the transformation map I'm going to use is this one. So that's going to be important. So in the case of this problem, we're going to have this, right? Where I filled in my values for A, B, H, and K specifically. And now I'm going to take the points from my graph and I'm going to transform them just like I would have in my geometry class. So the first point becomes -5, -1. And the next one becomes -3, -5. And so on and so forth. I get -1, -1. And my last one becomes 1, 7. Is everybody okay there? So all I'm left to do now is to plot these things. So let's see, -5, -1 is probably somewhere like there. And then -3, -5 is probably somewhere like down here. And -1, 1 is probably somewhere like there. And then 1, 7 is probably somewhere like up there. So then I just kind of plot my points. Is everybody okay with that? If you did this with graph paper, it'd be a lot easier to kind of see and everything would look parallel or whatnot, but I did it without a grid. So you're going to just have to live with a little bit of inaccuracy, you know what I mean? I think there's a way to put in graph paper into OneNote. Does anybody know how to do that? Yeah, how do you do that, Anthony? Rule lines? Ah, and you can pick, yeah, the type of grid you want. Medium grid probably would have been what I wanted. That would have made life a lot easier. I have to remember that. Thanks, guys. So that wraps up section 1.8. So you guys, for your problem set on Sunday, should finish up the rest of the problems in chapter 1. I can't remember what we left off at from the previous homework check, 18 or something. Something like that. Probably a lot of us did past 18, I noticed, in their homeworks, which is great. Your work is, like, do what you can when you can, pick away at it. So I think the last problem number in here is like 66 or something. But you guys are already asking me about stuff in the 40s, which leads me to believe that, like, we've done way past, like whatever the problem set was due last time. I've also, in the content library, put in the review packet. You don't need to start this over the weekend. I'll give you guys time in class next week to work on that. And we'll take some time in class, the following class period, to talk about or take questions from it and talk about what the test format's going to look like and that kind of thing. But I'm just letting you know it's there, that if you get like mega bored over the 5-ish day weekend, I know that Thursday's a virtual learning day or whatever, but the 5-ish day weekend, you're like, man, I need to do some math. It's there for you. I would tell you, like, maybe you should go outside and take a walk or get some sun or, do something active. But if you really need to do it, like, it's there. Or if you have a particularly hectic week next week and you're like, I just need to get a jump on things because I'm losing my noodles, stressing out about stuff, like, I get it. So it's there. Yes, sir. Of course. You're welcome. But yeah, that's kind of the story. And you guys, the test should be